Bismillahirrahmanirrahim. Assalamu alaikum. This is lecture number 18, and today we are going to start our new chapter, a new uh, portion of basic mechanical engineering. Basically, heat and mass transfer is complete course in mechanical engineering department. Not even in one semester, they are studying in two different semester. Heat transfer one and heat transfer two. So it's a very lengthy course, but still, for combination of these courses in BME, we just get the relevant numericals from the heat and mass transfer regarding your uh, civil engineering, especially in building infrastructure. Like we already discussed in the introduction of BME, there is a very vast application in heat transfer in building infrastructure. Due to the sun, due to the solar radiation, we are getting trapping heat inside the buildings, inside homes, etc. So avoid this or reduce that heat trapping. We have different material which reflect back heat and not getting trap out in the homes, etc. So calculating how much amount we can save and what should be the thickness of that material, we will study in this heat and mass transfer subject. Okay, so let's move on. Still this. Yes. Basically, heat transfer is a form of energy that can be transferred from one system to another as a result of heat temperature differences. Like in one surface, we have a temperature like 40 degrees centigrade, another surface we have a 20. There will be heat transfer from high temperature to lower temperature. Um, the science that deal with the determination of rate such energy transfer is called heat transfer. We already study heat transfer in thermodynamics, but with the different concern. For an example, in thermodynamics is concerned with the amount of heat transfer as a system undergoes process from one equilibrium state to another, and it gives no indication about how long the process will take. Like we already calculated the amount of heat transfer in the form of in the Q, in the symbol of Q. From the energy balance equation, delta E is equal to Q minus W. So the Q will be heat transfer, but it will be related to equilibrium from one state to another. How much the heat is released or how much the heat is taking by the system or from the system, that we are calculating in the in the thermodynamics. But how much the heat transfer will take time period, and in the steady state, we already we have solved the numericals in thermodynamics regarding steady state, not unsteady, that heat is completely transfer in one state to another, but in between there will be heat transfer. There will be unsteady condition, that the parameter is changing with respect to time. So in heat transfer subject, we are calculating, we are studying this unsteady system of the uh, unsteady systems. Thermodynamics deals with the equilibrium state change from one equilibrium state to another. We already discussed this. Heat transfer, on the other hand, deals with the system that lack thermal equilibrium, and thus it is non-equilibrium phenomena. Okay, continuously heat transfer from high temperature to lower temperature, and there will be non-equilibrium phenomena. For an example of human body, the human body temperature is around 37 degrees centigrade, and the ambient temperature surrounding us would be from 22 to 30 degrees centigrade. So there will be continuous heat transfer from our body to in the air by the different modes: conduction, convection, and as well as radiation. We have many application of heat transfer, like car radiator. The IC engine of the car or motorcycle car radiates the heat through radiator into the environment. The air conditioning system, it is also absorbing heat from inside room and giving out at outside of the air, as we discussed. The circuit board of the computer, power plants, and refrigeration system, these are all the application of heat transfer. Okay, again, we have we already studied thermodynamics, so it is very easy that uh, all the energy, like for an example, this is soda can bottle, it has a lower temperature and outside there will be high temperature. So heat is this soda bottle is absorbing heat from outside air. Okay, so the amount of heat is absorbing will be q is equal to mcv delta t. We normally studied that formula in the form of enthalpy, mh2 minus h1, but there will be also a different formula that is mcv delta t, the heat transfer rate, and cv is a specific heat at constant volume, and the specific heat is a simple, by definition it is amount of heat required to raise 1 degree centigrade per unit mass. It is a specific heat, and if the process will be at constant volume, there will be term cv, and if the process at constant pressure, there will be term of cp. So we didn't solve the numerical by this formula, but you can also solve the numericals related to the air, the duct and heated air numerical. We can solve this numerical with this formula, but not with the steam. We also solve numerical of steam. So, but for the steam, we stick to the steam tables, and the formula is equal to m h2 minus h1. Okay. So in a stationary closed system, the change of internal energy, there will be no kinetic potential, so the all the energy change will be internal energy, and the internal energy formula would be mcv delta t at a constant volume. Okay. Now comes towards the heat transfer mechanism. You already studied this mechanism in inter or metric. The basic mechanism are conduction, convection, and radiation. All modes of heat transfer require existence of temperature difference. All the modes are from higher temperature medium to lower temperature one. So it is a convention that we relate the transfer of heat from high temperature to lower temperature, and we apply the same convention in our these numericals of conduction, convection, and as well as radiation. Okay, we will learn we start with the conduction and then convection and then radiation. So by the simple definition of conduction, conduction is the transfer of energy from more energetic particle of a substance to adjacent particles that are less energetic due to the interaction between the particle. Okay, you can see that in this picture, and the conduction takes place in all phases of the substance, like in solid, gases, and liquid, but the more prominent are in the solids. So you can see the pictures that if it is a solid body, the molecules in the solid body are interacting with each other with the vibration. They are not freely moved in the volume. So all the molecules stick into their places, but they do vibrate with the adjacent molecule. And in the metal we have a free electrons. So these free electrons can conduct electricity as well as heat. The same way the metal is conducting electricity, in the same way the metals especially are very good conductor of heat as well as. So they are transferring heat by the interacting another adjacent molecule by simply vibrations. And the free electrons in the liquid, they are free to move from one position to another, so they are also transferring heat from collision of the molecules, and when the vibration of the molecule, the heat transfer takes place, is called conduction. But when the molecule goes from one place to another and transfer heat, it called convection. There will be difference. So when the molecule, due to the diffusion of molecules, or heat transfer will be convection. But if the molecules interact with other adjacent molecule and transfer the heat, it will be called conduction. So conduction also take place in liquid as well as in gases. but you have to understand the concept that interacting with adjacent molecule, and the result of that the heat transfer take place, so it called conduction. But when the molecule they are free to move, so one molecule goes to another place and transfer the heat, it will be called convection. Later we will discuss convection with more videos, etc. So in the gases and liquid, conduction is due to the collision and diffusion of the molecules during their random motion. In the solid, it is due to the combination of vibration of the molecule in a lattice and the energy transport by free electron. Because this definition well define the conduction in gases, liquid, and solid. In the solid, the molecules are fixed in their lattice molecules, so they can only transferred by the combination of vibration motion. But in the liquid or gases, they are free to move, and due to the collision and diffusion of the molecules during the random motion, that conduction transfer take place. But keep in the clear, but keep your concept very clear. When the molecule goes from one position to another without the collision, or in that collision it will take the transfer heat take place. But when the molecule goes from one point to another and transferred into the another surface, then it will be called convection. Later we will discuss in detail. So I also attach some interactive video on it.
Transfer of heat, conduction. Objectives.
See that
to see the different
the actual amount of heat transfer in the starting. Yes, the conduction is more prominent in solids, especially in metals. So this is the experiment. This kind of experiment also takes place in our mechanical engineering lab of heat transfer. In this way, you can see that this is the solid bar. Any metal bar, like it can be brass, it can be iron, it can be copper, silver, etc. The wax place here, and we place with the nail. When we start to heat this metal rod, the conduction take place in this direction. The heating is goes from this direction to this direction. So this by dropping of this nail indicates the conduction direction, how fast the conduction is passing over here. The wax place here in that position, it melts, and due to the melting of wax, the nails will drop down. So by simple this experiment, we can also compare two different metals. Like if we fixed a brass rod, and with the comparison with the copper, uh, the faster the nail will drop will be the better conductor of heat. Like for the brass and the copper, which will be the better? The copper. The values of the thermal conductivity of copper and brass is very similar, but the brass is better conductor of heat than, copper is better conductor of heat than brass. And if we place a wood, the nail will not drop down, because the wood is a bad conductor of heat. Even the wood will burn, it will flash itself due to the lower flashing point. So the wood will burn, but it will not transfer heat from one point to another in the conduction, because it has no free electrons. The wood will be heater to the closing point, but before conducting to the till the end of the point, it will start burning. It will goes into the flash point. So this is basically the video that shows how the random motion of a solid with the heat transfer take place. Like the molecule are fixed in the structure, lattice structure, and due to the random vibration motion, it is transferring heat from one point to another. And due to the free electrons, the conduction takes place very rapidly. You see that? free electron interacting with other molecules, and just due to that in metals the transfer of heat, conduction heat transfer take place very rapidly, and they very have a good thermal conductivity, and the non-metals don't have free electrons, due to which only the random motion, the heat is transferred from one point to another. But in metals there will be a random motion as well as free electrons. So you can compare, like second example is for water. If we heat up the water, it's analyze. Yes, now if we heating the liquid, uh, the water molecule passing over there due to the high energy value, and between there will be conduction as well as convection, but the convection is higher than the conduction. The molecules are interacting with the adjacent molecules and colliding with adjacent molecules. You can see this picture as well as that, gaining that temperature, higher kinetic energy, it moves upward, and going towards upward it also collide with another adjacent molecules. So when they are uh, transfer heat by colliding other adjacent molecules, that the transfer of heat take place is again the conduction. But when the say one molecule pass from to the another point, it will be convection, like in this picture. Yes, when it when the molecule is going from this point to this point, if they collide with adjacent molecule, the transfer take place is conduction, and when they move upward with the higher temperature values, it will be convection. Okay, so in liquid and gases the convection is dominant. The molecules are moving very rapidly with a very high speed, so the convection in the liquid and gases uh, is more than conduction, or is prominent. So we can only study convection in gases and liquids. Okay, so let's move on. This, I hope this will be interesting video for all of you. Now to study conduction, we have to know the numericals. We have to know the equation which deal with the conduction. The Fourier law of heat conduction explain the equation of conduction heat transfer. By definition, it is the rate of heat conduction through a layer of constant thickness delta x is proportional to temperature difference delta t across the layer of the layer and the area normal to the direction of heat transfer, and is inversely proportional to the thickness of the layer. Like for example, this Coca-Cola bottle, we have a high temperature outside, and we have a very small thickness layer of the metal, and the heat is transferred from this point to this point, from surrounding air to cola bottle. So the outside layer of the bottle, it is contacting with the air and has a high temperature, and it has a lower temperature. So the heat is transferred from this point to this point with a very low thickness. The thickness will be delta x, and the heat transfer is directly proportional to temperature difference. The higher the temperature difference, higher will be the conduction heat transfer rate. Like we have a temperature like ambient temperature 30 degrees centigrade, and the refrigerated cola bottle is in like 16 degrees centigrade. So we have a difference of 14 degrees centigrade delta T. So if we make higher temperature difference, the higher conduction transfer will take place. That's why the equation will be the rate of heat conduction will be directly proportional to temperature difference. Secondly, area. You can see the area as well as from this picture. Larger the area, this is the area of the Coca-Cola bottle. Larger the area, the larger will be the heat transfer. Smaller the area, smaller the heat transfer take place. In this picture it is not very visible. You can see in this picture as well as. Yes. Let's suppose we have a square metal plate. Here we have a higher temperature, here we have a lower temperature. So in metal there will be conduction. So the temperature, the Q, the heat transfer rate is directly proportional to temperature and the area. You can see the area. If we increase the area like this one, the temperature, the transfer of heat take place, it will be bigger. If we increase further more area, the transfer of heat take place will be further higher. So you can see that the transfer of heat transfer rate will be directly proportional to area. Okay, and area will be perpendicular to the direction of heat transfer. You can see this, the area will be perpendicular of the heat transfer. Okay, and it is inversely proportional to thickness. You can see the thickness, this is the thickness of the plate. If the thickness of the plate will be increased, it will resist the temperature goes from higher to lower. So definitely it will be irreversible, inversely related to heat transfer rate. So the rate of heat transfer conduction is directly proportional to area, the temperature differential, but inversely related with the thickness. And by removing the proportionality, we have to place some constant, that is thermal conductivity K. Okay, K will be the thermal conductivity of the material, which is the measure of ability of material to conduct the heat. Okay. So area will be in our hand, the temperature difference will be our hand, but the K will be the universal property of the metal or any solid object. Okay, it has a universal capability to conduct heat from one point to another. Like for the metal, the thermal conductivity will be very high. It will be very they have a very high capability to transfer heat from one place to another, and capability or ability. So the K value of the metal will be higher, and the K value will of the non-conductors or insulator like wood, like like carbon, like fibers body, like we have a better insulation of um, uh, ra- uh, uh, polyurethane that is placed in the refrigerators, and like rock wool and glass fiber, etc. Later we will also discuss the type of insulator used in construction material, by which you can save lot of energy that will be wasted in trapping of heat and then cooling the room by air conditioning system, ACs and central air conditioning system, etc. So now we learned the yes, we learned the equation of conduction heat transfer. It is minus Ka dt by dx, and in you already understand in a lot of numerical we have to apply integration. So it is in the form of dt by dx. But making it this numerical very simple, we can take the temperature difference and the thickness difference. Okay, like in this case, like in this case or in this case, this is the comparison of a copper and silicon. The thickness is same, we have a temperature is same 30 20 30 20, the thickness is same 1 meter, but due to the change, due to the thermal conductivity of two different solid body, we have a different heat transfer rate. Like for the copper, the K value is 401 watt per meter degree centigrade. So the heat transfer will be 4010 watt per meter square. But in the case of silicon, the K value is 148 watt per meter degree centigrade. So it has a 1480 watt per meter square. So it has a lower heat transfer rate. Okay. And one thing you can ask in the numeric in the equation, that there will be minus sign. What will the need of the minus sign in this heat transfer rate to make this the quantity of heat transfer will be in the positive. Okay. If we take the temperature difference, or if we use the simplified formula of heat transfer rate, then we don't need to place minus sign. Like if we taking the temperature difference, like 30 minus 20, and the thickness is 1 meter, but so we don't need to take minus sign. But if we are making it with the integration and differentiation formula, we have to take the values from the origin. So when we used to the values taking values from the origin, they automatically there will be the minus sign. So to counter that minus sign, we have to place minus q is equal to minus ka dt by dx. I just give you an example. Like you can take this make this just yes draw the bar. Like if we heat transfer taking place from this point to this point, and we have a origin, this is 0, this is like 4 meter, so the distance is 1 meter. There will be there will be thickness of metal. Okay. So if we take the upper limit minus lower limit, the temperature taking place from this point to this point, we have a like 10 degrees centigrade, and we have like this 2 degrees centigrade. So the temperature difference of upper limit is 10 minus 2, and the upper limit of the the upper limit of the temperature will be 2 minus 2, and the lower will be 10. And in this the distance, the upper limit will be 4 and the lower limit will be 1. So 2 minus 10 will given the answer in the negative sign, in the negative value. So to counter this negative, we have to place minus sign over there here. Okay. So we only use that minus sign when we are solving the equation with the differentiation and integration. But keeping the values, keeping the simple formula, and keeping the difference values, like difference of thickness, difference of temperature, so we don't need the minus sign. We just take the formula Ka delta T by delta X. Okay. So let's move on. These are the different this is the graph taken from the book Sangil. It shows the thermal conductivities of different materials. Like we have materials in normal room temperature, in the solid phase, in the liquid phase, and the gaseous phase, like the air, the argon. The dotted line is for the gases. You can see that you can see the behavior of the different material or different substance, that the gases in the gases, the thermal conductivity will be increased with the increase of temperature. So in the lower temperature, the thermal conductivity of the gases is lower, but in the higher temperature, the thermal conductivity of the gases is even larger. And by logical means, you can understand it by simply, at higher temperature the molecules have high kinetic energy, so it has more capability to for offer diffusion and collision of the adjacent molecules. So it has a very high capability, it has high capacity of thermal conductivity as compared to lower temperature. But still the gases are are bad conductors, having a bad thermal conductivity. So they are bad conductor of heat as well. You can see the values in the points range. Even at the higher temperature, at the higher temperature, you can see that the values of gases are lower. Now comes to the liquid. Liquid is higher thermal conductivity value as well as with the gas, so they are better conductor of heat as compared to gases, but still the conduction of water still has a lower value as compared to solids. Okay, so then we comes to the solids, and in the solids we have a different solids. Some are good conductor and some are not very good conductors. So we have a lower values of fuse cards and pyrocrene glass. Glass is also a very bad conductor of heat, so they have a low heat conduction capability. After that we have aluminum oxide, then iron, platinum, then aluminum, then gold, then copper, and then silver. Silver has a very higher thermal conductivity, so it has a very high capability or ability to transfer heat from one point to another due to the adjacent motion of the molecules in the solids. After that, we have a higher value of thermal conductivity in diamonds, in different forms of diamonds. So diamonds also a very good conductor of heat in the conduction. So these are the about the thermal conductivity, the universal properties in the materials, in the metals, in the gas, in the different forms of materials, in the gases, liquids, and solids. Another definition of in thermal conductivity or in heat transfer, it is a thermal diffusivity. Diffusivity. By simple formula, you can understand it is represented by the alpha, and it is directly proportional to the heat conducted, and inversely proportional to the heat stored, and the formula of thermal conductivity over heat capacity. Okay, raw Cp is heat capacity. It is simply the uh, tell us about the absorption of heat due to the conduction. If the material values of alpha, if the alpha values of the material is higher, it means it is a very good conductor of heat, and it will not store heat much. But if the alpha value is lower, it means that the heat stored capability of the material will be higher as compared to heat conducted, so the material can absorb heat much than transfer from one point to another. So you can compare the value of diffusivity, like wood, we have a very lower value, 0.1310 p power minus 6. So we have a very low value of wood, then beef, then water. So they, all of them, glass wool, heavy soil, they they are not, they are bad conductor of heat, and they absorb heat but they do not transfer from one point to another. That's why they have a very lower value of alpha. The amount of heat they store more heat than conducted, so alpha value is lower. Contrary with the metals, we have a different values and opposite values. They have very high values. So in metals, the capability of heat storing is lower as compared to transfer. there, Therefore the alpha value is higher in metals and the good conductor of heat, and alpha value is lower in the bad conductor of the heat. You can simply imagine with the or compare this parameter or terminology with the absorption of the heat due to the conduction. So we have taken, so now we have one numerical, a very simple numerical. We have 6 to 8 minutes to solve this numerical, and I think we can solve the numerical easily. It's a very simple numerical. Okay, it is example of 1.5. the cost of heat loss through a roof. You can see that there's a room, there's a house, and we have a concrete roof over here. Uh, let's let's read out the numerical first. Then I just explain. The roof of an electrically heated home is 6 meter long and 8 meter wide. So 6 meter and 8 meter will be the area of the concrete roof, and 0.25 meter thickness, and thickness will be this 0.25. Okay. uh, and made of a flat layer of concrete whose thermal conductivity is zero point 0.8 watt per meter degree centigrade. The temperature of the inner and the outer surface of the roof one night are measured to be 15 degrees centigrade and 4 degrees centigrade respectively. So the temperature inside the house will is 15 degrees centigrade, or you can see the inner layer of concrete. The inner layer of concrete roof will be 15 degrees centigrade, and the outer temperature of the outer layer of the concrete roof will be 4 degrees centigrade. So it is a scenario of winter season. This house is heated by electrically heater, as tell us in numerical. Now we have to measure the rate of heat loss through the roof, that in the night, that how much the heat is losing from this roof only for a period of 10 hours. And we also have to calculate the energy, like in 10 hour how much the energy will be lose, that is generated through uh, electric heater. Secondly, we need to calculate the cost of heat loss to the homeowner if the cost of electricity is zero point 0.8 kilowatt per kilowatt hour. Okay, so let's just solve this numerical. Um, just goes to the data over here. So let's close this picture. In data we have delta T, how much 15 degrees centigrade, 15 degrees centigrade minus 4 degrees centigrade. And keep in mind that in it is degree centigrade. Okay, and keep in mind that we always take a higher value of temperature to the lower value, even in the minus negative temperature. And the thermal conductivity, the unit of thermal conductivity in degree centigrade, so we keep the temperature in degree centigrade, not in the Kelvin. So 15 minus 4 is 11 degree centigrade. We get the delta T, and we have a area. How much the area? Let me see, like 8 by 6. Okay, 8 by 6 meter, so it will be 48 meter square. And thickness, we have delta x is 0.25 meter. 0.25 meters. So now in the next slide we just apply the formula. Q is equal to K A delta T by delta x. So the thermal conductivity value is 0.8, area is 6 by 8, that is 48, and the temperature difference will be 15 minus 4, that is 11, and it is 0.25. So by solving this you get the answer 1690 watt. So by solving this we should apply this dot 2, because it is heat transfer rate. The value will be in 1690 joules per second or watt. So we can apply this 1609 watt. or 1 point, if you divide by 1000, so we can get the value 1.69 kilowatt or kW. now now we have to calculate the amount of rupees that will be lost during the heat transfer rate. This amount of energy is losing only from the roof, not from the walls of the house. Only from the roof in one night, this amount of energy is losing in only 1 hour. So they are telling about 10 hour. Okay, so for a period of 10 hours, and they have electricity unit 0.08. So in Pakistan, the electricity unit is around, for the commercial or residential, we have a 17 rupees. Now they increase 3 rupees, so it will be 9. But we take the Pakistani value, so more it so make it more practical as per current scenario or current region. Now now we have to calculate the energy. The energy is simply uh, heat transfer rate multiplied by time, or power into time. The unit is power is watt. So 1.69 multiplied by 10, that is 16.9 kilowatt kilowatt hour. Okay, this is the energy consumption in 10 hours. And you know what, you can get the k electric bill. The unit of the electricity will also in the kilowatt hour, and we have 17-18 rupees, but in the USA, or where the numerical has been taken, the unit is $0.08 per kilowatt hour. So we know the per kilowatt hour cost that are our disco is supplier, uh, is charging for the electricity. And we know the amount of heat loss from the roof. Then we can easily calculate the cost. Okay, so the cost will be, we have a 16.9 kilowatt hour. All the meter in your house is also calculating this unit, and in the bill they simply multiply this unit with the unit quantity of electricity. That is, if we take the normal Pakistani rate, it is 17 rupees per kilowatt hour. So we multiply by 17 rupees per kilowatt hour. So kilowatt hour will be cancelled out, and only you get the rupees. It is around 287.3 rupees. Oh, so you can imagine that in one night, in 10 hours, the roof is only uh, taking cost around 287.3 rupees in 10 hours. So you can imagine the cost for the whole month. If we multiply with the 24 and multiply with 30 days, you can get the cost for the whole month, that how much the heat is losing just for the one roof. So whether it is in the winter season, we lose the energy in the form of heat, and in the summer season we lost the energy in terms of heat trapping from outside of the sun or temperature, and keeping the lower temperature lower due by the refrigeration system like air conditioning system. So by this numerical, you can also capable to calculate amount of rupees you have to pay for the month, for any motor, for any heater, or for any air condition system. Like for AC, the 1 ton AC is taking around 1 kilowatt hour, one thousand watt or 1 kilowatt in 1 hour. So you can multiply with, if you run this AC 6 hours, multiply by 1 kilowatt into 6, that there will be 6 unit daily, and multiply by with the 17 rupees, you can calculate the amount of energy for one day that can be reflected in the month of this K electric bill. So till then, we have today we have learned conduction, one numerical. So in the next week we will learn convection, radiation, and so on. Till then, Khudafis, take care.